Hi, and welcome to Boyer-Moore algorithm. So what is Boyer-Moore algorithm? The Boyer-Moore algorithm, as the name suggests, was developed by Robert S. Boyer and J. Strother Moore in 1977. It is an efficient string searching algorithm and has served as standard benchmark for string searching algorithm ever since. The Boyer-Moore algorithm takes a backward approach, so pattern string is aligned with text string and then compares the character of a pattern from right to left, beginning with the rightmost character. So, Boyer-Moore is a combination of two approaches, the bad character heuristic and the good character heuristic. In bad character heuristics, upon a mismatch, we shift the pattern until either A, the mismatch becomes a match, or B, the pattern moves all the way past the mismatch character. So, let's have an example. So let's say we have this text string, then we have this pattern string. So, according to the Boyer-Moore algorithm, we start comparing them from right to left, beginning with the rightmost character of the pattern. So, we compare, starting with the rightmost. So, we check if it's a match or a mismatch. So, since it's already a mismatch, according to the bad character rule, the mismatch becomes a match. So, we shift the pattern until the mismatch becomes a match. So, we shift it, alright, and then we start comparing it again, starting with the rightmost character again. So we see if it's a mismatch or not. Since it's a mismatch again, we shift the pattern again until the mismatch becomes a match. So we shift the pattern again. So see if it's a mismatch or not. So it's another mismatch. So we start shifting again until we find a match for the mismatch. So we stop and then we compare again. So we just keep repeating the process of comparing and then seeing if it's a mismatch and then we shift the pattern until the mismatch character from the text becomes a finds a match character from the pattern. Okay, so in here we found that we have a mismatch, but there are no more characters left from the pattern that can match from the mismatch character in the text. So in this case, we shall use the other rule, which of the bad character rule, which is the pattern um, shifts or all moves past the mismatch character. So we shift the pattern until we move past the mismatch character. So we shift it, and then after that we compare again from the rightmost character and see if it's a match or mismatch, and then we determine if that character is still available from the pattern. So if it is, then we just make the mismatch become a match, and so we shift it. If that character from the string, the mismatch character from the text, is not found anywhere in the pattern anymore, then we move the pattern all the way past that mismatch character because, well, we cannot find a match for it in the pattern anymore. So that's how the bad character rule works. In good character heuristics, upon a mismatch, we let T be the substring that is matched, and then we skip until either there are no more mismatches between the pattern and T, or either the pattern moves all the way past T. So, let's have an example for the good suffix rule. So let's say we have this text and this pattern. So we compare again from right to left, and as we can see, there are some characters that matches, and then we come across a mismatch. So according to the good character rule, we let T be the substring that is match, and then we skip until there are no more mismatches between the pattern and T. So if we find a T again that occurs in the pattern, so we match them. So we shift the pattern until they match. So we shift, and there we go. So we start comparing again. So we compare again from right to left, and as we can see, there are now more matches. So upon a mismatch, so we let T again be the substring that is matched, and then we either shift the pattern until there are no more mismatches between pattern and the T, or the pattern moves all the way past T. But if there is at least one character in T that matches with the pattern, then we shift the pattern until that T matches with the pattern. And then, as we can see, we already found the pattern. So, we only skip past all the way past T whenever the match substring T doesn't occur, or we cannot find it anymore in the pattern. So if that happens, then we skip the pattern all the way past T. So how do we determine if we're going to use a bad character heuristic or good suffix heuristic? Well, we can determine that by if we start comparing, and then if there's immediately a mismatch between the two, then we use the bad character heuristics. But if we compare and then we find multiple matches, then we use the good suffix heuristics.
So for the approximate string matching, we chose the Hamming distance. Hamming distance is a fundamental tool for measuring the dissimilarity between two strings or two pieces of data. It calculates the number of position of which corresponding elements differ. In this first example, we have two strings, which is Hamming and the other one is shaming. First, we will identify the characters that matches in these two strings, which is M, I, N, and G. So after we identify the similar characters, now we will compare the other characters and try to apply the replace operation, which is part of the edit distance. And we have three operations in edit distance, which is insert, delete, and replace. For this case, we will use replace since strings has the same length of characters. So now we will replace H with S, and the next one is A with H, and the last one will be A with M. Now we have made three edits for this one, which means the Hamming distance of this string is 3. Now let's have an example that has a different length of characters. We have algorithm and rhythm. For this example, we have 9 characters on the first string and 6 characters on the second string. Now, as I said earlier, we have 3 operations, which is insert, delete, and replace. For this example, we will use those 3 operations. And first, we will identify again similar characters, which is R, T, H, and M. Second, we will delete A, L, G, and O, which will give us 4 edits already. Now, the first string will become R, I, T, H, M. And here, we will use the replace operation. And now, we will replace I with H, and now it will give us 5 edits. And for the last operation, we will use insert. We will insert Y, in between H and T. And to conclude, we will have a total of 6 edits for the string 1 algorithm to transform it into the word rhythm. Now, Hamming edit distance of these two strings will be 6 because we did 6 edits of characters. That will conclude the Hamming distance the Hamming distance of those 4 strings.
For the time complexity of Boyer-Moore, it is represented as big O mn, where m is the length of the pattern. This can be considered as somewhere in between linear and quadratic time. This occurs when all the characters of the text and pattern are the same. While for the time complexity of Hamming edit distance algorithm, it is big O n, or linear time. The time complexity of the algorithm is directly proportional to the length of the string.